guys, welcome back. I'm here to do a request on this problem that you see here. So let's go ahead and get started. Alright, as you read the problem, they mention photons. In the reading you see here, it says 1 photon of argon and krypton laser has energy. So they mention photons, they mention energy, and then they talk about frequency of the photon. Sounds like a little bit of Planck's constant. So we're actually going to use the equation that involves the energy of a single photon. So let's go ahead and write that equation down. That way we have it ready and available to us. The energy of a single photon is E equals H times V. H is Planck's constant. If you don't know what Planck's constant is, it's a constant. You have to memorize it or maybe have it on a resource available to you. Here it is. H equals 6.626 times 10 to the negative 34 joules times a second. Now, if you don't have this written down somewhere, please write it down and keep it handy, because you're going to need it anytime they mention photons and energies and frequencies. You're going to need it. Okay, so memorize it. Alright, anyway, they also give us an energy value up here. Alright, there's a problem with this. If you look at the units for Planck's constant is in joules times a second. Joules, that's the key word. Not kilojoules, but joules. We need to convert that number over. So over here, I'll show you the easiest way to convert this always back to a standard unit, and that's just to get rid of the prefix. So watch this. I love when numbers are already in scientific notation. It helps. Alright, we have energy of a single photon is 3.499 times 10 to the negative 22nd. Okay, but you see where it has this kj? I'm going to drop off the k. Okay, now I'm not going to drop it entirely, but I'm going to get rid of that k. And the way that I can get rid of that k is by writing times 10 to the third. Okay, now what that does is that gives me similar bases here. Okay, the base is 10. So since the bases are the same, if you multiply, you just add your exponents. Okay, so really then, this energy that we have here is E equals 3.499 times 10 to the negative what? Well, negative 22 plus 3 is negative 19. So it's negative 19 joules. Alright, so we have successfully converted our energy from kilojoules into joules, making it usable for this problem. Now what we need to do is we need to substitute in Planck's constant into H and the value of E in for E, because that's for a single photon. Alright, but before I do substitution, I usually try to go ahead and solve for the variable. Since I'm trying to solve for the frequency, which is V here, I need to get the V by itself. Now on your equation, some textbooks use the letter L for frequency. This one, yeah, I'm using V. Okay. Anyway, so to get this V by itself, I need to divide both sides by H. In doing so, that'll get the V by itself. So what we have here then is frequency is equal to the energy of the single photon divided by, I'm sorry that Planck's constant was horribly written there, divided by Planck's constant. Okay, so all we need to do is substitute these numbers in. E was 3.499 times 10 to the negative 19 joules, divided by Planck's constant, which is 6.626 times 10 to the negative 34th joules times a second. Now all we need to do now is use our handy dandy cheetalator here. Alright, so we turn it on, we punch it in. 3.499. To do the times 10 to the negative 19, you hit second, comma, which gives you the small down, shrunken down e, which is the exponential form, meaning times 10 to the negative 19. Divided by, now what's our other number? Planck's constant, 6.626 times 10 to the negative 34. Now press enter. And here is my frequency. My frequency up to 4 sig figs is going to be 5.28. At first I want to write 0, but look to the right of the 0. There's a 7, so that's going to be a 1. So 5.281. But don't forget to keep looking towards the very end of the number. You see the E here? That means times 10. So that's going to be times 10 to the 14th power. Now let's check out our units here. The joules will cancel each other out, leaving us with 1 over a second. Now we all know that 1 over a second is the same thing as s to the negative 1, which is also the same thing as a hertz. So just to be good sports and to have proper manners in science, we will write down 5.281 times 10 to the 14th hertz, Hz. Okay? Now, that's fine and dandy. We're done with the first question, but now it's time to do the second question, because there's 2 parts to this. Okay? In this question, they wanted us to also calculate the wavelength. In order to calculate the wavelength, we need the wave equation. You may remember it from middle school and high school and even college. C equals lambda, which is wavelength, times V, which is frequency. And once again, V could also be F. It just depends upon the textbook publisher that you have. Now, remember that the speed of light is a constant. Okay, so the value of C is always 3.00 times 10 to the 8th meters per second. Now remember, they're asking for the wavelength in meters, so they want this. Okay, now just like earlier, we have to divide both sides by V, okay, to get the wavelength by itself. So that gives us wavelength equals C divided by V. We just need to plug these into the letters now, the variables, and we'll be done. C is 3.00 times 10 to the 8th meters per second. Now what was the frequency? We just calculated it. It is 5.281 times 10 to the 14th. Now instead of writing hertz here, that looks kind of weird, I'm just going to use the 1 over the S. The reason I do this is because the units up above have an S. It doesn't show hertz there, okay? Sorry, it doesn't. But anyway, I'm going to go ahead and cancel out the letters and stuff, the units, and see what's left. Notice that seconds cancel with seconds, so all that we're left with is M divided by 1 for our unit. So that's it. But I need to punch this into the cheetah later and get my answer. So I'll write it over here. Lambda is equal to what? Well, let's punch it in the calculator. 3.00. Now you could just type 3, that's fine. Times 10 to the 8th divided by 5.281 times 10 to the 14th. Now I'm going to press enter. And I get a number that's relatively small, and that's fine. That's correct. So that gives us 5.68, and at first you want to write down the 0, but look, to the right of the 0 is a 7. That's bigger than 5, so we get a 1 here. 5.681 times 10 to what power? Well, look, see if there's a power here. There is. There's an E. Times 10 to the negative 7. Now, what's the units again? That's right, it's in meters because we canceled out seconds. Meters. Finally, we have our wavelength. Okay. Anyway, this was a request problem. I hope that this was helpful. The only other tidbit information that I could give you to help you out is this. Notice how large our frequency is, and notice how small our wavelength is. Well, they have a relationship, believe it or not. Okay, move the calculator out of the way for now. Their relationship is basically this. If V, which is your frequency, is increasing, then your wavelength itself is decreasing. Okay, they behave, I want to say, oppositely. You know, they don't have the same behavior. If one increases, the other decreases. If one decreases, the other one will increase. So I just want to make you aware of that. So we usually refer to this as an indirect relationship, or inversely related, or indirectly related. So tying something again into your basic math classes, your Algebra 2, your Algebra 1, your geometry classes. But anyway, I hope that this was helpful. I hope that you get some use out of it, and try to spread the word, guys. Chemistry isn't all that bad. Y'all have a good night.